Hi everyone and welcome. In this video tutorial I would like to explain how to use Pyro. So here I'm going to first demonstrate how to install Pyro. I'm on this Linux system that I'm using here, and the first thing that we need to do is to activate the virtual environment that we have installed using conda. So this is done with conda activate and then the name of this virtual environment, which is CSB1021. So that switches environment. And now once this is done, I can use pip to install Pyro. And so the thing is that Pyro is not referred to as Pyro on the pip databases, but as Pyro-PPL, standing for Probabilistic Programming Language. So you press enter and the installation is relatively fast after this. We can now check that Pyro has been installed, so we start Python. We have here version 3.9, as I explained in the previous video. And if we do import Pyro, then after a few seconds, it should work. We can check the version, which is pyro dot underscore underscore version underscore underscore. And as of the recording of this video, Pyro is version 1.86 on Python 3.9. So this is it. This is what we need. Now we're good to go. We can use Pyro. First, I'm going to show the typical structure of a Pyro program. So I'm going to open this file that I prepared, Pyro nuts1, and we have here a typical structure of a Pyro program. You can see that this doesn't have to be long. We're talking of only 22 lines here. And we have the import section, the definition of a function here, and then a couple of functions that are used to run the inference. So we start with import Pyro and import PyTorch. So this happens all the time. We need these two modules to be able to do everything. So make a habit of starting all your programs with import Pyro and import Torch. Next, we define the model, which explains a little bit what are the variables, what are their distributions, and what are the variables that are observed and the ones that are not. So we're going to go through this particular model here, which has only two statements, assignment to a prob variable and assignment to a flip variable. Also observe that there is no return statement in that particular function. So this is something that's worth mentioning, is that the typical Pyro models are functions. They're Python functions, as you can see here, but it's not necessary that they have a return statement at the end. So let's go and see what happens. So we have here def model, which is the typical statement to define a function in Python. And we have an optional argument here, which is x. If you do not define x, it is equal to none. After this, we have the core of the function here, and we see that the first statement is a Pyro sample. So we create a Python variable called prob that is defined with this Pyro sample statement. So the first element of the Pyro sample is really the name that this sample has for Pyro. It's referred to as prob, the same as the variable name here. This is very typical. And the second thing that we need to specify is the distribution that we want this sample to have. So we're saying here pyro.distributions.uniform with low equals 0 and high equals 1. So we recognize here the uniform distribution, the standard uniform distribution, which means that every value between 0 and 1 has exactly the same probability as any other. So what happens between lines 5 and 8 is that we create a random sample with one value, which is called prob. And that value here, prob, can be anything between 0 and 1. In the second statement, we create a variable which is called flip. So when we see it's defined the same with a Pyro sample, the same as prob, and it's registered with the name flip here. So Pyro knows this as the flip sample. And as usual, I give the same name to the variable and to the way that this is registered for Pyro. And the distribution is pyro.distributions.bernoulli. So this is a variable which is discrete, and that's either 0 or 1. And the parameter of this distribution is prob. So prob here is that particular value, the one that was defined above. So here we recognize this example that we've given before, where we choose a value between 0 and 1, which is uniform, and that represents the bias of a coin, the probability that it would land heads, for instance. So we choose that number between 0 and 1, and then we flip the coin, and we flip it just once, and we see what happens. So in addition to these two lines here that were present in the previous Pyro sample statement, we have one more parameter here, which is obs equals x. So this specifies that this sample is observed. We have observed the value of the Bernoulli distribution, and it is equal to x. X is the parameter that we give to the model. So to recap, the model has got two random samples. The first here represents a value between 0 and 1, which is uniform, and the second represents a value that's either 0 or 1, and that represents the flip of a coin with the bias that's represented here with this prob parameter. So this is exactly the case that we've given before. Now to run the inference on that particular model, which means to know the distribution of prob once we have observed the values of flip, we're going to use simulations, and in particular we're going to use the NUTS simulation setup, which stands for no U-turn sampling. So all these simulations are types of Metropolis Hastings algorithms. Those are algorithms that use the Markov chain Monte Carlo setup to provide a random sample from the posterior distribution. So we need to specify how the model runs forward, which means to produce new values of x. You do this, then you do this. And after this has been done, now this little bit here will allow us to run the model in reverse, which means once you have observed this, what was prob, that is kind of compatible with the values that you observed here for flip. So the way this works is that we define an object of class pyro.infer.mcmc, and MCMC stands for Markov chain Monte Carlo. So we create an object that is small letters MCMC, and the first parameter here is pyro.infer.nuts, and then between round brackets model. So this is the line here that defines a kernel that encapsulates this model here and allows it to be run with the nuts sampler. This is really where most of the heavy lifting is done so that we can sample the posterior distribution here of prob given flip. Then we specify that we want 1,000 random samples. So we want a sample of size 1,000 value of prob here. And we also specify that we want 1,000 warm-up steps. So the warm-up steps are required for the Markov chain to reach the stable distribution, the stationary distribution. So we said that we are ready to sacrifice the first 1,000 random samples as we consider that this is the time that is required for the jumps to reach the stationary distribution. We are aware that the very first beginning, the first few steps that we're going to run are not necessarily going to be in the stationary distribution. They're just allowing to get there, and so we throw them out. And when we have run these first 1,000s that are kind of a warm-up to get to the stationary distribution, then we start sampling for real and we keep the next 1,000. Finally, we say num chains equals 1. We say we just want one chain. We run this only one time in parallel, and this is a very simple example that we've got here, so we don't need to run complicated analyses with multiple chains. So that here defines the setup that will allow us to run nuts, and once this is done, we just need to call run here, mcmc.run, and we specify here in this function the value of the observations, and we say that we have observed one flip and the value is 0. So that's a tails, that's a failure. We specify here that the value of ops is going to be equal to 0. And once this is done, we just ask Pyro to produce a little summary of the samples that were obtained. So this is it for the model. Let's see what happens when we run it. We just need to run Python with the name of the file in this case. So Python pyronuts1. It takes a few seconds to load, and after this it goes relatively fast. You can see that in just a few seconds it produces 2000 random samples, but it uses only 1000. The first 1000 have been thrown away. You can then see that in the output we have only the prob parameter here that appears. The other parameter, flip, is observed, so there's no need whatsoever to show anything about it. So we're only showing the distribution of prob, and bear in mind this is the posterior distribution of prob, so which means this is what prob is like when we have observed that flip equals 0. This is an example that we've treated, and we have given the theoretical answer, which is that when you have a coin and you choose randomly between 0 and 1 its bias, and you flip it and you observe a 0, now the probability of that bias is on average 1/3, and you can see that this is exactly what we obtain here. It's not always as exact as this case because we have only 1000 samples here, so there can be a little bit of random deviations, but overall mostly we're going to be quite close to the target, which is 1/3 here. So we see that on this very simple case we were able, with a simple Pyro program, to recapitulate this example that we've given with the coin. Now let's see a more complicated example with Gaussian distributions. So we open the script pyronuts2, and we see that the script has approximately the same structure here. It's got the same length, and this time we're going to have a slightly different model using Gaussian distributions. As usual, we start with import Pyro and import torch. Then we see that there's the definition of the model, and the bit here hasn't changed at all. This is exactly the same as in the other script. So let's look what the model proposes now. So first we have one parameter, the same here, x, which is an optional parameter. If you do not specify it, it's equal to none. And we see that the first statement here defines a variable that is called mu, registered here as mu through the Pyro sample statement. And you can see that the distribution is pyro.distributions.normal. So that's the Gaussian distribution. And here we specify that log equals 0 and scale equals 1, which means that this is the standard Gaussian distribution with expected value 0 and standard deviation 1. So basically here we pick at random a value of mu from the standard Gaussian distribution, which means that it's mostly close to 0, but with a little bit of deviations. Typically we can do 3 standard deviations to the left or to the right, which means that we expect the value of mu to be anywhere between -3 and 3, let's say, but to be much more concentrated around 0 than around the extremes. So that's it. We have here one random value of mu, and from there we define a new sample, which is observed, this one, which we call x. So we have this variable here that we call x, and we call the sample x as well for reference. And so this time the distribution is pyro.distributions.normal, so the same as above, but now log is equal to mu. So log is itself a random parameter, and scale is equal to 1. So we have a Gaussian distribution here from which we're going to draw multiple samples every time with that particular parameter mu being the same but being equal to the first value that we drew here. And we also say that this sample here is observed. Ops equals x, that refers to the parameter that we give here, which is the value that we have observed for the second random variable. So that particular model here corresponds to a case that we have seen in one of the video tutorial that explains how to perform inference when we have a couple of Gaussian variables. The first one here indicating the expected value of the second. So we know the answer. We know, depending on the values of x here, what we should obtain, and we can check with this simple program whether this is going to be the case or not. So this bit here with the lines from 15 to 20 is exactly the same as before. This is what we need to do to register here the model to be able to perform nuts on it. And you can see that this is just a couple of lines. And again, we define the fact that we want 1,000 random samples and that we're throwing away the first 1,000 here. Again, we said that we just want one chain because the model is really simple and we just want to check that we obtain exactly the same results with the theory as approximately with nut sampling. Then we run the model here and we specify the values of x that we obtain. So these are 1.2, 2.3, and 0.9. It could be anything. We just say that this is what we have observed here. So we run the sampler, obtain a couple of samples, and finally we call MCMC summary so that Pyro produces a little summary of what happened during the sampling, which kind of values were obtained. So let's run this model and see what happens. So again, it takes a couple of seconds to load and then it runs relatively fast. In just a couple of seconds, it has sampled the 2,000 random samples that we required here. And you can see that again, the sample here has only one variable, mu. The variable x is observed, so there's no need at all to show anything about it. We want the posterior distribution of mu given x, so the only parameter of interest, the only value of interest is mu. And we can see that the mean here is 1.09. If we refer to the theory that we have developed, because in this particular case we know the exact distribution of mu given x, the value should be 1.1. So we see that this is very close here. When we look at the standard deviation, which is the standard deviation of mu given the observation of x, we get 0.5, which is the exact value. The variance should be 1/4 according to our little formula. So the standard deviation should be 1/2, 0.5. We see that in this case, we got very close actually. The values that we obtain are very close to what we expect from the theory. So that shows that we can very simply produce samples here with very little knowledge of the theory that will be spot on. So the advantage of the theory is that we know that the distribution of mu here is Gaussian, but there is no confirmation of this fact by just taking the random sample. What we have is 1,000 values here of mu given these three values of x, and nothing stops us from requesting more. We can just keep requesting up to, let's say, 1,000,000 random values, and then plot the distribution of these values, and then we could see that clearly they look Gaussian. Of course, that would not be a proof that the distribution is Gaussian, but we would see the shape and be quite confident that this is something that is approximately a Gaussian. So with these two examples, we've seen how to create small Pyro programs and how to use the nut sampler to obtain samples from the posterior distribution. We have seen that these programs produce accurate results. Of course, there is some variation here, which is due to the fact that the samples are random, so there will always be some random fluctuations. But these programs run relatively fast, and they're not too complicated to write. So that's it for now. More from me soon.